Over the past 10 years at the archive, the most common question we've received from viewers about the planet Nibiru is this: how could the Anunnaki survive on a planet that moves so far away from the Sun during parts of its orbit? To explore how humanoid life could inhabit a rogue planet with an elliptical orbit that only periodically brings it near a solar system's habitable zone, aka the Goldilocks Zone, we must address multiple astrophysical, geophysical, and biological factors. Of course, this is a speculative but scientifically grounded inquiry involving concepts from planetary science, astrobiology, and thermodynamics. Let's begin by defining some of the parameters. A rogue planet, also referred to in the literature as an interstellar planet, nomad planet, or free-floating planet, is defined as a planetary mass object that does not maintain a stable, gravitationally bound orbit around a host star. These bodies either formed in isolation through the collapse of molecular clouds, similar to sub-brown dwarfs, or were ejected from their parent systems due to dynamical instabilities, such as gravitational interactions with other massive bodies or stellar encounters. In this context, we focus on a quasi-rogue planet, which represents a hybrid case, an object that is primarily unbound or loosely bound to a stellar system, often following a highly eccentric orbit. An elliptical orbit is a type of Keplerian trajectory in which a celestial body, such as a planet or satellite, follows a closed, oval-shaped path around a central gravitational focus, typically a star rather than a perfect circle. The shape of the orbit is defined by its eccentricity, a dimensionless parameter ranging from 0, which is a perfect circle, to values approaching 1, which is a highly elongated ellipse. This configuration causes the planet to undergo periodic variations in both velocity and solar irradiance as it travels along its orbital path. When the planet is at perihelion, it receives significantly more solar radiation due to its proximity. Conversely, at aphelion it receives much less, potentially resulting in dramatic fluctuations in temperature and climate, depending on atmospheric conditions and thermal inertia. The Goldilocks Zone, formerly referred to as the Circumstellar Habitable Zone, is a theoretical region around a star within which a planetary body can maintain surface temperatures conducive to the stable presence of liquid water, a key prerequisite for life as we understand it. This concept is fundamental to astrobiology, planetary science, and exoplanetary research, as liquid water is considered essential for biochemical processes associated with terrestrial life. The CHZ is a guiding metric in the search for potentially habitable exoplanets. Missions such as Kepler, TESS, and the James Webb Space Telescope target planets within the CHZ for atmospheric characterization. However, the discovery of subsurface oceans on icy moons like Europa and Enceladus challenges the surface-centric paradigm, suggesting habitability may extend beyond classical zones under the right internal conditions. A rogue or semi-rogue planet like Nibiru faces three major obstacles to sustaining life: lack of continuous stellar energy, thermal instability, and photosynthesis limitation. When a planet like Nibiru follows a highly elliptical orbit that takes it far from its parent star, such as our Sun, it experiences significant fluctuations in the amount of solar energy it receives over time. This is a direct consequence of the inverse square law of light, which states that the intensity of light, and therefore heat, diminishes rapidly with distance. As Nibiru moves away from the Sun, the amount of solar radiation it receives drops dramatically. For example, if a planet doubles its distance from the Sun, it receives only 1/4 of the solar energy. At vast distances, such as several hundred astronomical units, the solar energy available becomes negligible, possibly less than that received by Pluto. A planet with an elongated or highly elliptical orbit, such as the proposed trajectory of Nibiru, would experience severe thermal fluctuations as it moves closer to and then farther away from its parent star. These shifts between intense heat during perihelion and extreme cold during aphelion create what is known as thermal instability. The rapid alternation between warm and cold climates would make it difficult for any stable biosphere to evolve or persist. Species adapted to warmth may die off during extended cold periods, while cold-adapted organisms may not survive the temporary warm phases. Freezing temperatures could cause glaciation, expanding ice coverage over the planet's surface. As the planet moves closer to the Sun, rapid thawing could result in massive flooding, coastal erosion, and soil destabilization. The cyclical expansion and contraction of ice could also create structural stress on natural formations and habitats, leading to geological instability, for example, landslides and earthquakes. Atmospheric gases behave differently under extreme temperatures. Prolonged cold phases might freeze out atmospheric components, reducing pressure and breathable gases. Then, during the warmer phase, violent re-evaporation could lead to volatile weather patterns including massive storms, high winds, or sudden climate swings. This would make long-term climate regulation nearly impossible without advanced technological intervention. One of the most significant challenges to supporting life on a planet like Nibiru, especially one that travels far from its star or exists in deep space, is the absence or extreme limitation of sunlight. On Earth, nearly all ecosystems depend on photosynthesis, the process by which plants, algae, and certain bacteria convert solar energy into chemical energy. This process forms the base of the food chain, supporting everything from microscopic organisms to complex animals and humans. If a planet spends long periods in deep space or in the far reaches of a solar orbit where sunlight is faint or non-existent, photosynthesis would be severely compromised or entirely impossible. Without light, plants and algae would be unable to produce energy. The traditional energy pyramid would collapse. And oxygen generation, which is a byproduct of photosynthesis, might be minimal or absent, posing additional challenges for aerobic life forms. Despite these challenges, several scientifically plausible mechanisms could enable humanoids such as the Anunnaki to exist. Notwithstanding the extreme cold of interstellar or distant solar environments, planetary bodies may sustain internal heat due to several natural mechanisms. These internal energy sources can create localized conditions suitable for life, particularly beneath the surface. If the planet possesses one or more moons, or is periodically influenced by the gravitational field of a nearby massive body, such as a neighboring planet or star during perihelion, tidal forces can induce internal friction within the planet's mantle and core. This friction results in tidal heating, a process where mechanical energy is converted into thermal energy. Tidal heating is well documented in our solar system. For example, Io, a moon of Jupiter, exhibits extreme volcanic activity driven by tidal forces from both Jupiter and its neighboring moons. In the case of Nibiru, if it were accompanied by a large moon or passed near massive celestial objects during its elliptical orbit, significant internal heat could be generated and sustained over geological timeframes. Planets form through the accumulation of smaller bodies called planetesimals, through processes that release gravitational potential energy, converting it to thermal energy during collisions and compression. Even after billions of years, residual heat from the planet's original formation may still exist, especially in massive bodies with thick mantles and slow rates of heat loss. This slow cooling can maintain a molten or semi-molten core, which contributes to ongoing geothermal gradients. One of the most consistent sources of internal heat is the radioactive decay of long-lived isotopes such as uranium-238, thorium-232, and potassium-40. As these isotopes decay over time, they release energy in the form of heat. This process, known as radiogenic heating, contributes to the sustained warmth of a planet's interior, particularly in the mantle and core regions. Earth's internal temperature profile, for example, is significantly influenced by radiogenic heat. Even if surface temperatures are inhospitably cold due to distance from the sun or lack of atmosphere, internal heating can create habitable environments beneath the planet's surface. This is most plausibly expressed through the formation of subsurface oceans. A thick outer layer of ice, potentially several kilometers deep, can act as a thermal insulator, preserving the heat generated below. This insulating effect reduces heat loss to space and maintains the stability of a liquid water layer underneath. The concept is supported by analogs within our solar system, for example, Europa, Jupiter's moon, believed to host a global subsurface ocean beneath 10 to 30 kilometers of ice. Another example is Enceladus, Saturn's moon, which exhibits geysers that suggest subsurface water reservoirs. In these subsurface oceans, liquid water could persist even without solar energy, opening the possibility for chemosynthetic ecosystems. These ecosystems would rely not on photosynthesis, but on chemical energy from hydrothermal vents or reactions between water and rock. Life forms in such environments would be independent of sunlight, similar to extremophiles found in Earth's deep oceans. In this scenario, Nibiru's surface temperatures could be extremely cold, approaching cryogenic levels, but subsurface environments might remain thermally stable and life-sustaining due to geothermal and radiogenic heat. Such a model challenges the traditional Goldilocks Zone criterion for habitability and suggests that life may be more resilient and versatile than previously assumed. For a planet like Nibiru, habitability may not be a constant state but a cyclical phenomenon. These intermittent windows of habitability, referred to here as thawing periods or thermal seasons, could occur when the planet approaches its perihelion. Depending on orbital mechanics, such a thawing phase might occur every few hundred to several thousand years, and could last for decades to centuries, depending on orbital velocity and distance. During these relatively brief periods of solar proximity, cryogenic surface layers such as ice sheets, frozen lakes, and subsurface permafrost could begin to melt, releasing liquid water across the planet's surface or into deep reservoirs. This influx of water could lead to localized or global hydrological activity, including rivers, lakes, geysers, or even temporary oceans. More significantly, the presence of sunlight and liquid water could reignite biological systems that lay dormant during the cold epochs. Life on such a world would likely operate on vastly different timescales than we're used to on Earth. Instead of daily or seasonal cycles, ecological and evolutionary rhythms could unfold over millennia. Civilizations, if any, may enter hibernation or deep stasis, awakening only during viable epochs. And evolutionary leaps might be driven by intermittent pressures, where survival hinges on success during brief, fertile windows. Orbit-induced thawing periods offer a compelling explanation for how life could exist on a rogue or distant planet like Nibiru. Through a combination of brief habitable windows near the host star, biological adaptations to long-term cold, and explosive ecological rebounds during thaw periods, a planet that seems inhospitable by Earth standards could, in fact, support a highly specialized and temporally adaptive biosphere. In this view, habitability isn't about constant warmth but about cyclical opportunity, a rare and fleeting season in which life awakens, feeds, grows, and sleeps again. One of the most plausible mechanisms by which life, intelligent or otherwise, could persist on a planet with a distant and highly elliptical orbit is through the presence of a thick, heat-retaining atmosphere. Such an atmosphere would act as a thermal blanket, insulating the planet's surface and significantly extending its habitable potential, even during the long periods when the planet is far from its parent star and outside the conventional habitable zone. A dense atmosphere composed of greenhouse gases such as hydrogen, methane, or carbon dioxide could trap infrared radiation emitted by the planet's surface, producing a strong greenhouse effect. This effect would retain solar energy absorbed during the closer parts of the orbit and slow the rate of heat loss when the planet is far from the star. Such insulation could maintain surface or subsurface temperatures above the freezing point of water for extended durations. In certain conditions, carbon dioxide can exist in a supercritical state, neither liquid nor gas, under high pressure and moderate temperatures. A supercritical carbon dioxide atmosphere could have unique thermodynamic properties, enabling efficient heat distribution and storage. This kind of exotic atmospheric composition could help maintain relatively stable surface temperatures even in the absence of continuous stellar irradiation. It could also provide a buffer against the harsh vacuum of space and radiative cooling during the outermost parts of the orbit. Other exotic atmospheres, possibly containing ammonia, sulfur dioxide, or trace greenhouse gases, might function similarly, depending on the planet's mass, gravity, and atmospheric pressure. A thick, dynamic atmosphere would also facilitate the redistribution of heat across the planet's surface through atmospheric circulation. This is critical in reducing temperature gradients between the side facing the star when closer and the side in shadow or during the extended winter phase of the orbit. Jet streams, convection currents, and planet-wide weather systems could transport warmth from equatorial regions or geothermal hotspots to colder latitudes. This atmospheric heat circulation can also prevent localized freezing and stabilize ecosystems, even if the overall energy input is relatively low. In more advanced scenarios, if the planet has an ocean beneath an icy surface or subsurface habitats, a thick atmosphere could ensure that internal heat remains trapped long enough to sustain liquid water environments, a key ingredient for life. In summary, the survivability of a species like the Anunnaki on a rogue or distant orbit planet like Nibiru could be made feasible through the presence of a massive insulating atmosphere. This atmosphere would not only trap and redistribute heat during the planet's solar flybys, but also act as a shield against the cold vacuum of deep space, allowing stable temperatures either on the surface or within protected subsurface biospheres. Such a configuration represents one of the most scientifically plausible explanations for habitability on a planet that spends much of its time far beyond the classical habitable zone. This brings us to another frequent question we encounter regarding the Anunnaki. Why did they need Earth's gold? In an exotic planetary environment like that of Nibiru, a civilization might leverage aerosolized particulates, including gold dust, as a component of climate engineering or natural atmospheric phenomena. Here's how fine gold dust could contribute to atmospheric insulation. Gold has unique optical and thermal properties. It is highly reflective in the infrared spectrum, especially mid and far infrared wavelengths, which are dominant in the heat radiation emitted from the planet's surface. If suspended in the atmosphere, fine gold particles could reflect outgoing thermal radiation back toward the surface, enhancing the greenhouse effect. This would create a radiative insulation layer, similar in concept to how clouds or volcanic aerosols can trap heat. In physics terms, this involves the scattering and absorption of cross-sections of metallic particles, which depend on their size, shape, and distribution relative to the wavelength of emitted radiation. Dispersed particles, metallic or otherwise, in a planet's upper atmosphere act as aerosols which influence climate in two opposing ways. One is by creating a cooling effect by reflecting incoming solar radiation, which is known as the albedo effect. The other is by creating a warming effect by trapping outgoing infrared radiation from the planet. If engineered or naturally balanced, gold dust could be optimized to maximize infrared reflectivity and minimize sunlight reflectivity, creating a net warming effect, particularly important during the planet's distant phase from the star. Gold has a high thermal conductivity, but in nanoparticle or microdust form it behaves differently than in bulk. If suspended in a dense atmosphere, gold particles might absorb and re-emit thermal energy slowly, increasing the thermal inertia of the atmosphere. This slows the rate of cooling between orbital perihelion and aphelion, effectively stretching habitability over longer timescales. Gold is electrically conductive and resistant to corrosion, which might allow it to play a role in blocking or moderating solar wind or cosmic rays, especially if ionized into plasma-like conditions in the upper atmosphere. It can also play a role creating reflective or absorptive atmospheric layers similar to Earth's ionosphere, helping retain atmospheric mass and energy in a thin magnetosphere or radiation-rich environment. If the Anunnaki or another intelligent species had the technological capabilities, they could theoretically seed the atmosphere with engineered gold nanostructures or dust particles to regulate heat retention, control atmospheric pressure dynamics, and buffer orbital extremes. This mirrors speculative Earth-based geoengineering concepts like using sulfate aerosols or metallic particles to counteract climate change. While the notion of a species like the Anunnaki surviving on a rogue or elliptical orbit planet such as Nibiru may seem implausible at first glance, a deeper examination reveals that such survival is not only theoretically possible, but rooted in known astrophysical and biological principles. Through mechanisms such as a dense heat-trapping atmosphere, orbit-induced thawing periods, geothermal or tidal heating, and advanced adaptive biology, including hibernation, energy storage, or subterranean habitation, life could persist even under extreme orbital conditions. To summarily dismiss this possibility is not a defense of science, but a refusal to engage with its speculative frontier. After all, life on Earth has already shown remarkable resilience in the face of radiation, freezing, isolation, and time. In a universe as vast and varied as ours, the outright rejection of life, especially intelligent life, adapting to conditions unfamiliar to us says more about the limits of our imagination than the limits of reality. So, the next time you have an armchair pseudo-astrophysicist lecture you on how intelligent life on Nibiru is an impossibility, direct them to this video. It could possibly clear up their fog of cognitive dissonance, or at the very least, shut them the hell up. Thank you for watching this video till the end. If you enjoyed this content, please take a moment to like, subscribe, and share. It truly makes a difference. As a channel that is over a decade old, the archive has seemingly been shadowed by the algorithm, so we rely on your direct support more than ever. To those of you already supporting through Patreon or as channel members, thank you. You're helping keep this research alive and independent. If you'd like to join us and help preserve forbidden knowledge and ancient truths, check the links in the description. Until next time, stay curious and stay awake.